We have been able to analyze and design this reinforced concrete structure. We have also done the slab design. And in this video, I'll be showing you everything you need to know concerning the foundation design of a reinforced concrete structure using the software ProtaStructure. This foundation design will be based on pad footing. I will show you all the settings that you need to do in ProtaStructure to perfectly carry out your pad footing design. And I will also show you when a footing should be doubly reinforced and when it should be single reinforced, and many more things to come. So having successfully designed our structure, next thing to do now is to come to this story level, which is foundation level. I'll double click on story 0. Yes, this is what I'm having. Let me turn on my grid line, let me turn on my axis and everything. So I'll come to display, I'll come to layer, I'll turn on, I'll click on ghost axis, plane definition, and also test. So I've have everything turned on. So let me, okay, so I'm having this. We have already done the interactive design. We have carried out the interactive design. So I want to remove this design status. So I'll come over to display, come over to visual interrogation. I'll scroll up, click on none, and click on OK. So right now our aim is to design our foundation. But first, before I start designing your foundation, there are some settings that you need to do in ProtaStructure. So I'll come over to my setting tab, I'll click on it, allow it, let a dialog box will appear. I'll come over to foundation. So I'll come over to foundation. So once I appear here, so soil unit weight, generally soil unit weight is 18 kilonewton per cubic meter. So but I'm having that the allowable stress of my soil, allowable stress of soil is my own. In this case, that's soil bearing capacity. From the design report, from the soil report, I'm having it to be 120. Then you leave everything here as default. If you want to you can come and change this soil vertical subgrade coefficient. But before you change it, you should know that you should have a very good knowledge about this subgrade coefficient, because and if you want to get a very good knowledge of it, you can go to Joseph Boyce and get a very good knowledge of it. But if you don't know anything about it, you can just leave it at default. So we'll leave it at default for now. So we'll come over to ring concrete thickness. So this ring concrete thickness is just known as, it's just serving as your binding. That's your ring concrete, just like binding. So in this case, I'll be using 50. I don't want to use 100. I'll be using 50, and I'll also be using 50. So I'll just leave this one as default because we are not carrying out strip foundation design here. Then default pad footing form. I would like it to be square. I like it to be square. So I'll leave everything here the way it is. Then I'll come over to this side, leave it as default. Then I'm now having minimum footing width. That's the minimum width of your footing. I want to leave it at 1000. Then coming to minimum pad base depth. So coming over to minimum pad base depth, that's the depth of your foundation. Sorry, the depth of your footing. I would not like it to be 400. I would like to choose something like 250. I would like to be using 250. That's it, to be my minimum footing depth. Okay, fine. Let me use. I want 300. I want 300. So I'll go with 300 to be my minimum depth, minimum footing depth. Then coming over to maximum steel bar spacing, I'll leave it at 250. I'll leave it at 250. But I know, remember what I told you, that even also in footing, since because of quality, I always like to go with the spacing of 200. So for that, I'll just do 200 because I know that 250 will pass. In fact, let me just leave it at 250. Then doing detailing, I will now use a spacing of 200. So coming over to size increment, I'll still leave it at 100. Yes, I'll save it at 100. So both the depth increment, I'll save it at 100. What do you mean by size increment? For example, size increments, what it means is that assuming I'm to use colon of 1200, and if 1200 fails, it will increase by 100, which that means the next colon size they will provide for me is 1300. But if I should leave the size increment to be 50, that means if 1200 fails, the next column size they'll suggest to me is 1250. Yeah, so for me, I don't like all these 50 at the back. I always like it to be a whole number, like a complete whole number, 00. So I would like to be 100 size increment. Then concrete cover, I'll like my concrete cover to be 50 millimeter. Then coming over to this, I'll just leave it at default. Then coming over to this point, uncheck this, use top bar. Don't use top bar in our pad footing. We don't normally use top bar. The only time that we use top bar in pad footing is if it is a combined pad footing. If it is a combined part footing, that means that's when we'll be using top bar because there will be moment. But if it is not a combined part footing, don't use top bar. But don't worry, we'll still explain this thing more later on. Then coming over to minimum steel bar. So me, I would like to be using steel bar of 16. Oh, it's true. Remember, I am doing our when we are editing material, I chose 16, but I'll go back and select 15. I'll go back and select 12 because I want to use the minimum table of 12. I'll go back and select 12. So with all these things, I'll come here and click on OK. So once I click on OK, I'm here. Then I'll now come over to analysis again. Come over to building analysis. I want to edit my material. Come over to this point. I'll come over to foundation. So I'll shake since I'm having sand there. I'll leave it here because from the report from the soil report the soil report says that it is sand, so I'll leave it here. So the foundations the concrete strength of foundation, I would like to be using 20/25, which is 20 Newton per millimeter square. Then coming over to steel grade, I would still like to be using a steel grade of 460. Yes, it's still okay for me, 460, but I want to use my foundation. I want my foundation to be Y12, sorry, Y12. Then if it fails, let it now go to Y16. I'll write the minimum to be Y12. Then if it fails, let it go back to Y16. I'll click on OK. I'll then click on OK, and then click on OK again, then click on close. Then I'll now come over to my setting again. I want to increase. I'll come up to foundation. I would like to use minimum to be Y12, even for distribution. I would also like it to be Y12. Then I'll now come and click on OK. So right now, I've successfully done my settings and everything. Next thing now is to design the column. So to design my column, I'll just click on this. Once I click on it, I'll right click, then click on insert part footing. I'll click on insert part footing. I'll click on it and wait for it to be designed. So let's wait for it to be designed. It's coming up, it's loading. This thing is that he's designing this part footing. Yes, the dialog box will appear once it's true. Once it's true with the design. So look at it. Design is successful. So design is successful. So coming over, look at what we gave up at a depth of 300, which is what we choose as our minimum depth. I'm having a concrete cover to be 50. Yeah, I'm having the concrete cover of 50, which is what we choose. So this is what this is what the design gave us. So after design, I'm having that I should be having a square footing of 1400 millimeter by 1400 millimeter. So I'll come over to this point if you want to see the 3D view. So come over to this one, see it. So this is what I have. So if you see that it is not doubly reinforced, yes, it is not doubly reinforced because we unchecked that part of doubly reinforced. So it's not doubly reinforced. So as me, you want to see your column load, this is where you will be seeing your column load. You come and click on column load in case you want to design it manually to verify what the software gave you. So you can come here and pick the load coming to this column and design it. Then come over to rebar. So coming over to rebar, assuming that it is a combined footing, assuming you're having a combined footing here now, we will now click on I will now click for you to add top reinforcement in both directions. So let's zoom, see. So it has included a top reinforcement, but this is not a combined footing. So we'll uncheck this and we'll also uncheck this. But if it's a combined footing, it must have a top reinforcement. It is a must. It must have a top reinforcement for it not to fail. It must have a top reinforcement. Okay, let me just explain it like this. You know how Alright, I'll start by first explaining the basics, which is why must the tension zone in every beam be reinforced. As we all know, if a uniform distributed load or even a point load is being applied to a beam, that beam will be subjected to tension and also subjected to compression. Look at it, the bottom part will be subjected to tension, while the top part will be subjected to compression. What do we mean by tension? We mean by tension in the sense that it will be stretched apart, and compression in the sense that they will be coming together. And as we all know, concrete beams or concrete in general is totally weak in tension. So because once it is being subjected to tension, it will stretch apart, and which will result to failure. So for that reason, in every beam we always reinforce the tension zone, because concrete is very weak in tensions, and once a beam is being subjected to any load, this tension zone is prone to failure. So that is why in all our beam we always reinforce our tension zone. Then coming over to a cantilever, as we have explained before, that concrete is very weak in tension. If this is a cantilever and we apply a load at the extreme, if you can see, the top part will not be the one in tension, while the bottom will not be the one in compression. In the sense that once we apply a load to this beam now, it is the top part that will be stretched out. And if the top part is stretched out, it's this stretched part that is now in tension. And if it is not properly reinforced, it will it will fail from this tension zone because concrete is generally weak in tension and very good in compression. This compression zone will not fail, but as a result of this tension zone failing, it will not result in this compression zone also failing. So in other words, to counter this thing, in cantilevers, we do provide reinforcement at the top portion, while in beam we do provide reinforcement at the bottom or at the bottom portion, but it is only applicable to simply supported beam. But in continuous beam, the support parts are being subjected to tension, but we'll still explain that later. But I just want you to understand that once it comes to a cantilever, the tension part is the one subjected to tension, and once it comes to a beam, that's simply supported beam, the bottom part is the one subjected to tension. And two, concrete is very weak in tension. That is why we always reinforce the tension zones. So let's now coming over to combined footing and isolated footing. So I'll explain using this diagram below. But first of all, let me explain combined footing before going over to isolated footing. So first, this is the footing base, which is this one on green color. Why this is the column, and two, this column is transferring its load to this footing base. And so look at this point load now. This point load means column. This point load is something as this column. It is transferring its load to this footing base, which is this one on green color. Then we are having this uniform distributed load is the soil. It will try to resist the load that this column base is being transferred to it. So why this one's now is just the way this beam, this footing base will deflect under this column load. That's this ones, and then this ones. It's just the way this footing base will deflect under this load. So let me explain it now. So if this column transfer its load to this beam will deflect like this, meaning that this top part will be under compression and this bottom part will be under tension, meaning that we'll have to reinforce this bottom part. Coming over to this point, the only load being applied to this footing base is this soil, which is this UDL. So this UDL will try to deflect this beam upward like this, meaning that this top part will now be under tension, while this bottom part will now be under compression. Take note, at this point now, this top part is under compression. Why this top part is under compression? Why this bottom part is under tension? Why at this point this top part is under tension and this bottom part is under compression? Meaning that within this portion we need to reinforce this top part. We need to reinforce this top part because it's this top part that is under tension. While coming over to this point now, this column load will cause this thing to deflect downward, meaning that this top part will be under compression and this bottom part will be under compression. So look at this is the bending moment diagram. This is the feedback diagram of this. Then this is the bending moment diagram of it. So that means we're having moment at the base, moment here, and also moment here. So for that reason, we will reinforce the bottom to counter for this moment, and we also reinforce the top to counter for this moment, because this top part is the one under tension. And wherever we're having tension, that means we'll be having moments there, because wherever we're having tension, we'll be having moment there. See here, the tension zone is the bottom. That's why we're having this tension zone. That's why we're having a moment here, because the tension zone is at the bottom. So in this combined footing, we will reinforce the top zone to counter for this moment and reinforce the bottom zone to counter for this moment. While coming over to isolated footing, in isolated footing, this is the column. This thing is the column. This is the footing base. While this is the soil serving as a UDL. So this is how this footing base will deflect once this column load is being applied to it, meaning that this bottom part will be subjected to tension and this top part will be subjected to compression. Meaning, remember, concrete is very weak in tension. We'll only reinforce this bottom area, leaving this top area. So this is the bending moment diagram. So if you see in isolated footing, there is no need to reinforce the top, because there is no moment on the top, there's no moment at the top, only at the bottom. So that's why we reinforce. That's why in isolated footing we will reinforce the base, not the top. While in combined footing, we will reinforce the base and the top too to counter for this moment. Okay, let me just click on OK. Okay, we are through with the design. So I'll just come here and click on OK. So if you see now, this is what we're having. So coming over to the design of this, I'll just click on it, then click on insert path footing. I'll wait for it to design. Yeah, it's designing. So look at it, design completed. So I'm having this. Then if I also want to label it, I can just call it I can just call BT1. Yes, BT1, because this one is 1200. The other one I have is 1400. But normally for the labeling, I normally leave it for my detailing. Once I'm detailing, I will label everything once. I'll not bother myself labeling it here. So this is how you just do it for all your column footing. Wait for it to design. This is what we are going to do throughout. Then we look out to have 1300 by this. Since we are not having combined footings, that means it is only single reinforced, not double reinforced. So let me come and do the ones this one. I click again, I'll do insert path footing. I'll do insert path footing. Let's wait for it to design. So this is what we have in now. Look at it, 1400. So say you click on OK. Let's wait for it to appear. Then we'll now click on this one again. I click on insert path footing. We'll click on insert path footing. Yeah, I'll click on insert path footing 1600. Yes, I think this is the column that we're having the highest load on. So let's go and check again. Let's click on OK. So let's check again. So you see that the part base they provided for this one is 1600, which is very more. So let's go and check our analytical model again. I'll click on view and I click on building analytical model. I want to know whether is this column that we got that was carrying the highest load. So if you come now, look at it, is that column? Yeah, look at it. This column that is having, because we have said that the ones on blue, means that they are carrying a very high load. The load, look at, for example, this one's on blue, the load coming to it is 193 kilonewton. That's the load coming to it. Then the ones on lead, look at it, the load coming to it is 13.1 kilonewton. And to that, if you see, they are the ones on lead and this one, the ones on lead and on orange, they are mostly placed at the edges. Yeah, because they are not really carrying slab on all direction. But these ones at the center, they are carrying slab on all direction. That's why the load coming to them is high. That's why their load is high. Look at it. And to this is the one we just designed now that we're getting there. The part base is 1600. If you see, the reason why the part base is 1600 is because the load coming to it is much. So let's go back to our story and finish up our design So I'll click on this, like click again, click on insert path footing. I'll click on insert path footing and wait for it to insert. Yes, so this is what we are having now. I'll click on OK. But right now, you can due to the length of this video, I will just pause and do everything. I will pause and do everything. So right now we have successfully designed all our path footing. We have successfully designed all our path footing. So coming to the 3D view, we'll come to the 3D view. This is what we are having. We have successfully designed them all. If you see, all of them are all on green. Means they have been designed and they are all passing. Also our slab, they are all on green. Means that they have been designed and they are all passing. Even our columns and our beams. So at this point, what we'll be doing now is to export this to ProtaDetail. So to export this to ProtaDetail, I'll come to drawings and report. Coming to drawings and report, I'll come and click on ProtaDetail. Then once I click on ProtaDetail, I'll allow it to load. It asks me, do you want to save the changes? I'll click on yes, I want it to save the changes. So I'll allow it to load. So while waiting for it to load, remember you can get the CAD file of the architectural plan used in this series of tutorial and practice on your own, because practice makes perfect. If you want to master anything, it's through practice and it's through repetition. It's through practice. The more you practice, the more you get to know. Remember, the architectural plan comes with the structural drawings. Yeah, in case after your designs, analysis and everything, after your design, I enter detailing. Once you encounter any challenge, you can easily reference the structural drawing that I did to be clarified on your issue. So right now, ProtaDetail is opening. Let's wait for it to finish up. Then we'll now extract our drawings. Or once it finishes, we'll now extract our drawings. So it's still loading. So yeah, it has opened. So this is the ProtaDetail interface. So you can come here and click on auto generate detail, or you can click on and start by creating a new drawing. So this is what I want. I click on start by creating a new drawing. So once I click on start by creating a new drawing, I'll first of all come to form plan. I'll right click. I want to, if I want to do one by one for foundation, for story 1 and for story 2, you'll be doing it one by one. But in this case, I want to do everything at once. So I'll right click on draw floor plan. Once a dialog box will appear, then I'll just come and click on OK. I'll click on draw. So I'll now locate a point where I will draw it and then click. So I'm waiting for it. Let's wait for it to draw. So this is how we are going. This is what we are doing now. We are trying to get all our detailing. Then after, we'll now go to AutoCAD using stone bridge detailing template. I'll still introduce it in our next video and perfect our detailing. Then coming over, normally I don't normally like using, I don't normally extracting column, but let me just extract it for the sake of this video. So I'll come and click on this, right click on draw column application. I'll just click on OK. I'll then locate this point. I would like it to have the drawing at this point. Let's wait for it to draw. Let's wait for it. So this is the column application. Then you can come and click on column elevation, right click. You can call normally I don't like to draw column elevation, but due to this video I'll also do it. Click on draw, then click on this point. Yes, it will successfully draw my column elevations for me. Then I'll click on it again, right click, draw column schedule. I'll click on draw. I'll then click on any point. So this is the current schedule. Then I'll click on story beam elevation. In this one, I normally like drawing this one by one. I'll not like to click on this. No, I'll just right click on story for it to do only story one. So I'll right click. Don't click on draw beam elevation one by one. No, it will take your time. Just click on draw beam elevation. Then come and click here. Click on draw. Then you move up. Well, I would like you to draw it here. Yes. So this is what I'm having. Let's wait for it to draw up. It's loading. It's loading. Let's wait for it. Yeah, so it has given me the drawing successfully. Then I'll come and click on for story 2. I'll not click on draw one by one. I'll click on draw beam elevation. I'll click on draw. I'll like to place it by the side here. So let's wait for it to draw. It's generating the drawings. It's generating the drawings. So let's wait for it. Then after this, we will now come and do our path footing detail. So we have to we will now come over to path footing detail. We'll right click. We will not click on draw one by one. We'll just click on this one, draw path footing detail. We'll click on it. Then we'll click on draw. We'll now come and place it here. So let's wait for it to draw. So yeah, at this point, since we have been able to extract all our drawings, then we'll now export it to AutoCAD. We'll export it to AutoCAD. Then we'll click on here, right click on export. Once you click on export, you now come and click change directory. So this point, you now pick a place where you want to save your file. So me, I'll just pick anywhere. I want to save it here. So I'll click on here, click on OK. Once I click on OK, I'll now click on export. So it will then go. Look at it, it is saving. It is saving. So once it's true, it will take us to the place where we choose for it to be saved. Then from there, we'll now open it in AutoCAD interface. So let's wait for it. Yeah, it's loading. It's loading. Yes, so this is what we are having. So this is what we are having. Look at the drawing one, but you can rename your own. Then you now double click on it. Once you double click on it, yeah, it's opening on AutoCAD interface. So you will now see our drawing. Click continue opening the WG file. So let's wait for it to open. Let's wait for it to open. Then you now see your look at our whole drawing. So these are our whole drawing. So right now we have come to the end of this video. In our next video, we will be doing the we'll be manually perfecting the details that the ProtaStructure have given us using this software AutoCAD, but we're making use of stone bridge detailing templates. But don't worry, in our next video I will get to introduce you to all this. So stay alert, because we will soon post our next video, so you learn more and get you and know more about engineering principle. So with this, I believe that you have learned a lot from this video. But don't forget, practice on your own. You can get the CAD file in the link in the description below, and the link is also pasted at the comment section.